Welcome to the deep dive. Today we're tackling rotational mechanics. We've got some great source material here. We're going to unpack the science behind, anything that spins or turns or uses leverage.
That's right. Think about how trains manage corners, or, maybe more surprisingly, how high jumpers clear the bar. It's all in here.
Yeah, exactly. And we're moving beyond just like simple pushing and pulling forces.
Definitely. Our main source is this really well-structured instructional summary on rotational motion. It gives us a clear path, from the basics of spin speed right up to complex stuff like conservation laws.
And it connects the physics to real examples, which is super helpful.
It really does. Makes the abstract concepts much more tangible.
We should also give a quick nod to where this structure comes from. It's part of a curriculum that highlights the work of physics teacher Hakkı Veli Torun. Really excellent stuff.
It focuses on understanding and applying the physics, not just memorizing formulas.
Okay, so let's dive in. Our mission really is to get a grip on these core ideas of rotational physics.
And a big theme that jumps out is how crucial distance from the axis is. It pops up everywhere.
Right. So first things first. How is moving in a circle different from just going straight? Let's break down speed.
Okay, yeah. So the moment something rotates, you suddenly have two kinds of speed to think about. Imagine standing on a merry-go-round.
Okay, I'm on a merry-go-round.
If that ride spins around once every, say, 10 seconds, everyone on it completes a circle in the same amount of time.
So everyone has the same rotation rate.
Exactly. That's the angular speed. We use the Greek letter omega. Omega for that. It's just rotations per unit time, and it's the same for every single point on that spinning object.
Got it. Same spin rate everywhere.
Think about how far you actually travel. If you're near the middle pole versus way out on the edge.
Ah, right. The person on the edge is covering way more ground in those same 10 seconds. Much faster.
That's the tangential speed, $5. This is the actual linear distance covered over time.
And the sources are clear. If one point is like 3 times farther from the center.
It has to be moving 3 times faster, linearly speaking, tangentially.
So the link between the spin rate, omega, and this linear speed, dollars, depends on how far out you are.
Precisely. It's proportional to the radius, $3. The formula's simple, $5 in omega. That radius, $3, is the key factor. It's the multiplier.
Okay, radius is the multiplier. Now, this is where it gets, well, really fascinating for me. Applying this to trains.
Ah, yes, the train wheels.
How does a train going around a curve manage the fact that the outer wheel travels a longer path than the inner wheel?
Especially when, and this is the kicker, both wheels are fixed solid to the same axle.
Right, so they must spin at the same rate, same omega.
They have to. So how does the outer wheel cover more distance without, dragging or slipping or just tearing everything up?
If they were just normal cylinders, it seems impossible. There'd be enormous friction.
And this is where the clever engineering comes in. Train wheels aren't actually perfect cylinders.
They're not.
No, they're slightly conical. They slope inwards towards the center of the track.
Conical, like a cone shape. That seems weird for stability.
It seems counterintuitive, but watch what happens on a curve. That outward sensation you feel, the centrifugal effect, it nudges the whole axle sideways just a tiny bit towards the outside rail.
Okay, so the axle shifts outwards.
And because the wheel is conical, when it shifts, the outer wheel now contacts the rail on a part of its cone that has a larger diameter, a bigger effective radius, $3.
And the inner wheel.
At the same time, the inner wheel shifts onto a part of its cone with a smaller diameter, smaller effective dollars.
So same axle, same spin rate, 2 mega, but different effective radii where they touch the rails.
Exactly. And since $5 omega, that difference in $2 automatically means the outer wheel travels faster tangentially than the inner wheel.
Wow, so the train literally steers itself using geometry. The cone shape adjusts the speed naturally for the curve. No complex steering needed from the driver for the turn itself.
It's dynamic self-correction, built right into the shape of the wheels. Pure physics elegance.
That's incredible. Okay, sticking with this idea of distance from an axis, let's switch from speed to force.
Rotational force, right?
Not all forces make things move in a straight line. Some make things rotate. And that rotational force, that leverage, that's torque.
Torque. It's the rotational equivalent of linear force. It measures how effectively a push or pull causes something to spin or changes its spin.
And again, distance is key. If you push right on the hinge of a door, the axis...
Nothing happens. Zero rotation. You need to apply the force away from the axis, and ideally perpendicularly.
Right. And the strength of that torque. It's the force you apply multiplied by the distance from the axis. the lever arm.
That's the one. Force times perpendicular distance. Torque, force x distance.
Let's use the classic wrench example, tightening a bolt. If I grab the wrench handle really close to the bolt head,
Tiny distance, tiny lever arm, you'll need a huge amount of force. Lots of effort.
but if I slide my hand way out to the very end of the handle,
Maximum distance. Maximum lever arm. Now, a much smaller, easier force can generate the exact same turning effect. The same torque.
so the distance acts like a multiplier for my effort.
It absolutely does. Reduces the required force dramatically. Our sources mention a seesaw too, right? A small child can balance a large adult.
If the child sits much further out from the pivot point, the fulcrum,
Same principle. Leverage isn't just about raw strength. It's applied physics, managing that distance.
okay, so we have rotational speed, rotational force.
Right.
What about the balance point? The point everything seems to rotate around?
Ah, the center of mass, or CM, sometimes called the center of gravity. They're usually the same place for objects near Earth.
Right, the CM. It's like the average location of all the mass in an object or a system.
Exactly. It's the point where gravity effectively acts, and it's the point that follows that smooth, predictable path, even if the object itself is tumbling wildly.
And the location of this point can be, well, pretty surprising sometimes, like in the high jump.
Oh yeah, the Fosbury flop, a brilliant example of manipulating the center of mass.
So jumpers, using the flop, they arch their backs incredibly as they go over the bar, head first, legs trailing.
And that extreme arch is the whole point, physically speaking. By arching like that, they actually cause their center of mass, the average point of all their body's mass, to travel underneath the bar.
Wait, hold on. The center of mass goes below the bar itself? How is that possible? That feels like cheating gravity.
It's not cheating, it's using physics cleverly. Think about older styles, like the scissors kick. The whole body, essentially, had to be lifted clear over the bar. The CM had to go significantly higher than the bar.
Okay.
With the flop, because the CM passes under the bar at the peak, the athlete minimizes how high they actually need to lift the bulk of their weight. They clear the bar while lifting their overall mass less high. It saves energy.
So they can clear a higher bar with the same initial jump effort just by rearranging their body shape relative to the axis of rotation at that moment. Amazing.
It's pure biomechanics and physics. And speaking of weird locations for the CM, it doesn't even have to be inside the object, does it?
No. That's another mind bender from the sources. Things like a donut or a C-shaped bracket or a boomerang.
For those shapes, the calculated average position of mass, the CM, is actually in the empty space. For the boomerang, it's sort of floating in the air inside the curve.
So when you throw it, even as the boomerang itself is doing all these complex spins.
That mathematically defined center of mass point out in the empty space is the thing following a perfect, smooth, parabolic arc through the air, just like a thrown ball would. It's the anchor point.
Physics is weird sometimes. Okay, so we've got speed, force, balance point. What about keeping something moving in a circle? What force does that take?
Right. To force an object out of its natural tendency to go straight, that's inertia, and make it follow a curve, you need a force pulling it inward.
Inward, towards the center of the circle.
Always inward. That's the centripetal force. $5, it's a real force. Think tension in a string when you swing a ball, or the friction between tires in the road in a turn.
Its strength depends on the object's mass, how fast it's going, and how tight the circle is. The radius.
Yeah.
Faster speed or tighter curve needs more force. Follow C as mv/r.
That's the one. It's the force required for circular motion to happen.
Okay, so when I'm in a car and it takes a sharp turn and I feel like I'm being shoved outwards towards the door, that's not centripetal force because that feels outward.
If that feeling, that outward push, is what we commonly call centrifugal force. But here's the tricky part. In a standard inertial frame of reference, like someone watching from the sidewalk, there is no outward force acting on you.
So what am I feeling?
You're feeling inertia. Your body wants to keep going straight. The car door is actually exerting a real inward centripetal force on you, forcing you to turn with the car. The outward feeling is an artifact of being inside the accelerating non-inertial reference frame of the turning car.
Okay. It's a pseudo-force, an effect of my own inertia relative to the accelerating car. The real force is the door pushing in.
Precisely. It's a crucial distinction. And understanding this difference is exactly how we can think about simulating gravity in space.
Artificial gravity. The sci-fi dream. Made possible by spinning things.
Absolutely. If you have a large space station, maybe shaped like a wheel or cylinder, and you spin it.
The outer wall, the floor, is constantly pushing inward on everything inside astronauts' equipment.
Right. It's providing that necessary centripetal force to keep everything moving in a circle along with the station.
And that constant inward push feels like gravity pulling things down towards the floor.
Exactly. It mimics the effect of gravity. The faster you spin or larger the radius, the stronger that simulated gravity feels, according to Phi-Theta equals mv2r.
But there's a trade-off, right? Spin too fast and people get dizzy.
Nausea, yeah. And if the radius is too small, the difference in the force between your head and feet can feel really weird, unnatural.
So the ideal solution, according to the sources, is a really large radius, like kilometers wide.
If you have a huge radius, say a couple of kilometers, you can spin it quite slowly, maybe just one rotation every minute or two, and still generate a comfortable, Earth-like artificial gravity without making everyone sick.
Big radius, slow spin. Again, it comes back to managing that distance, $2.
It always does. It's the core variable in almost all these rotational scenarios.
Okay, let's wrap this deep dive with the kind of grand finale principle, the ultimate law of spin that connects planets, skaters, divers, everything.
Ah, the conservation of angular momentum, a fundamental law of physics.
So angular momentum, we use the letter $. What is it, basically? Rotational momentum.
Sort of. It's a measure of how much rotational inertia an object has and how fast it's spinning. Think of it like the quantity of rotation.
Yeah.
And the law is beautifully simple. If there's no net external torque acting on a system,
No outside twisting force, no friction slowing it down.
then the total angular momentum, the law of that system, stays absolutely constant. It's conserved.
Okay, constant $.
Okay.
But to understand how things change, we need that other factor, moment of inertia, symbol $1.
Right. Moment of inertia, $, is the rotational equivalent of mass. Mass resists linear acceleration. Moment of inertia resists angular acceleration changes in spin rate.
And it depends not just on a mass, but how that mass is distributed.
Crucially, mass spread far out from the axis of rotation means a large $, lots of resistance to changing spin. Mass pulled in close to the axis means a small $, less resistance.
Got it. So angular momentum of the $, is the product of this moment of inertia,
Yeah.
or $, and the angular speed, omega. So L omega.
Exactly. And if $, must stay constant because there's no external torque,
And then if you change a $, omega has to change in the opposite way to keep the product $, the same.
and that brings us to the classic perfect example. The figure skater doing a spin.
Right. They start spinning maybe relatively slowly with their arms stretched way out.
Arms out, legs out, maybe. That means their mass is distributed far from the axis of rotation. Large radius, large $.
Then, whoosh, they pull their arms and legs in tight to their body.
Mass comes closer to the axis. Radius decreases significantly. Moment of inertia on $, drops dramatically.
And because dollars has to stay constant, if dollars goes way down,
Omega, the angular speed, has to shoot way up. They suddenly spin much, much faster.
just by changing their shape, no one pushed them harder.
It's pure conservation of angular momentum. Same thing for divers or gymnasts doing flips or twists.
They tuck into a tight ball, small dollars to rotate quickly in the air.
And then they open up, extend their bodies large $, just before hitting the water or landing, which drastically slows their rotation, omega, for a smooth entry or stable landing.
It's like they're constantly playing with their own $, value to control their spin rate. Omega.
Masters of manipulating $, to manage omega, all while $, stays constant.
You know, looking back at everything we've covered, conical wheels, wrenches, high jumpers, space station skaters, the common thread really is managing distance from the axis.
It really is.
Mhm.
Whether it's optimizing radius for speed or for leverage with torque, or manipulating it to change rotation rate via moment of inertia, distance is almost always the key variable you're controlling or dealing with.
Understanding that lets us design things or perform maneuvers that kind of defy our everyday linear intuition about how things should work.
Exactly. From smooth train rides to seemingly impossible athletic feats, and even making gravity in space, it's all applied rotational mechanics.
Okay, here's a final thought for you, something to maybe notice in your own world. Think about opening a really stubborn jar lid.
We've all been there.
If you're struggling, consciously think about where you're putting your force. If you grip right near the center, tiny lever arm, hard work. But if you shift your grip out to the very edge of the lid,
Maximizing that distance, trawlers from the center.
you maximize your torque. Feel how much less actual force you need to get that lid to start turning. It's the same principle we've been talking about right there in your kitchen. Leverage through distance. Something to think about.